our speakers.
Hi, everyone. Lisa Schwartz with Berkeley Lab. Thanks for returning. Today, we're focusing on distribution planning, modeling tools, and processes. And we have a great speaker, Enrique Chacon. He is at Electric Power Engineers. He's a manager for distribution planning, as well as distributed energy resource integration. He's a former distribution engineer at Southern California Edison. We also have, for our breakout rooms, Benjamin Lee, who's Director of Distribution Planning and Grid Modernization at Electric Power Engineers. He's got an extensive tenure at Southern California Edison as well, and his experience as a Director of Engineering at a utility engineering firm. So without further ado, here's our presentation from Enrique.
Alrighty, thank you, Lisa. So a pleasure to be here with everyone. So for the first part of the presentation, we're going to be going over distribution planning modeling tools as well as processes. So in terms of an agenda, we'll have an introduction, discuss some of the inputs and assumptions that goes into distribution planning modeling, give an overview of tools and methods, and also at the end, if there's any questions about any of the slides, please feel free to ask. I'll be more than happy to explain it in further detail. Okay, next slide. Okay, so let's talk about distribution modeling overview. So so what you see here on the screen is a sample screenshot from one of many distribution modeling softwares that are available. This one happens to be one from Synergy Electric, but all that distribution models are a digital representation of a distribution network's connectivity and demand. And what makes these models useful is not necessarily the graphical overlay, but more so the information that you feed into it. So none of this model is relevant without good and known and measured information that goes into it. So in terms of modeling types that you can do with these kind of softwares, you can do distribution planning modeling, you could do protection and coordination modeling, subtransmission and network modeling, and you can also do some dynamic modeling as well. And as I've kind of been alluding to, you can have these models, but if the accuracy or the underlying, if the accuracy or the inputs to these models are not great, it's going to significantly impact the results. So just really want to emphasize that that's going to be an important point. Next slide here. Okay. Now, I mentioned Synergy Electric just now, but here's sort of an overview or a menu of some of the tools that are available commercially. So from a distribution planning perspective, some of the popular ones we see here are Synergy Electric, Stime, Windmill, Power Factory, and OpenDSS. From a protection perspective, you have Aspen, ETAP, PSS Cape. And it should be noted too that the distribution planning tools, so something like a Stime or Synergy Electric, they do have planning tools and modules integrated into them. So just in case you were thinking about a software that could facilitate that, just know those distribution planning tools does have that feature set as well. From a subtransmission and networks perspective, you have PSSE, PSLF, PowerWorld, and PSS SynCal. And from a dynamic modeling perspective, we have PSCAD. So again, just an overview or a menu of tools that are available for modeling purposes. Next slide, please. Okay. All right. So distribution planning modeling process and resulting study. So the core concept here is essentially to establish a baseline truth or a state. Kind of the way that I think of this is you want to, anytime that system modeling has happened, I want to recreate an event or recreate a basic understanding of maybe some system characteristics, or maybe there's a date and a timestamp that I'm very interested in. So that's essentially the core concept of planning modeling, is you want to, in some instances, recreate historical, and other instances, and we can talk about this later, is create something that could be in the future. But the reason you want to establish the baseline truth or state is to then understand what need and changes are required, if any. You might run a baseline truth or a base case model, as we sometimes refer it to, and everything might be okay, which is validation that your system is okay and running as anticipated. Or the alternative is there might be something revealed to you where you need to take action, right? So in terms of when we talk about taking action, so some of the analyses or topics that are looked into when you do modeling are things like voltage drop or power flow. things like DER interconnections, so really looking at the impact of these DERs. Other things here are contingency analysis, so maybe not base case, but maybe perhaps a backup plan or a backup feed. Um, Likewise, with contingency analysis, you kind of have switching that goes in with that as well. And then the last point here is voltage optimization. So sometimes there's ways to better utilize your voltage, maybe use some control schemes or some other tactic to better utilize voltage. One of the common applications we see is trying to bring down overall energy consumption. So that's kind of where voltage optimization really fits that bill. So again, this is a core concept, and these are some of the analyses that are done in the power system modeling. Next slide. Okay, now what we're showing here is basically a high-level perspective of the modeling process flow. So at the very beginning, even before we launch a model, you can actually do the first few steps without uh, launching a simulation software. The very first thing is to collect the input data. And when it says there you have your first decision triangle there, or decision diamond, the question is the data valid? If it's not valid, then you would clean and update the data. Now, when we talk about data validity, some of the topics that come up, are there zeros? Are there nulls? When you look at the data, does something look abnormal? Are there significant outliers? Those are the sort of things that you would consider when you're seeking to validate data. Assuming that your data is great, then you can move over to the initial model setup. So that's where you take the input data and you're actually placing it into the power simulation model. And when you first run it, the question here is the base case model valid? Now, this one here is a little subjective, kind of what I refer to as a gut check. If you're expecting a nominal 120 volt out of, say, a circuit feeder, and you have 200 volts, that's a significant outlier, right? We could sit there and say, no, that's not a valid base case model, and we can investigate and propose whatever change or implement whatever change we need to get the base case to be in a state where we can proceed and execute a study. And that's going to be important because if your base case already has errors, then any study that you do afterwards is not going to yield any uh, confident or even positive results. So assuming you have a valid base case model, we'll execute the study. And based on that study execution, then you can generate your results, reporting in whatever template, method, or format that you best see fit. So again, that's sort of the modeling process flow here. Very high level, but I think it's a pretty useful diagram. Next slide here. Okay, now let's go ahead and talk about inputs and assumptions. So next slide. Okay, so if you look there on the bottom, you have the distribution modeling circle, right? So what goes into it? There's a lot more that goes into it, but I would say this is a pretty good or pretty comprehensive high-level overview. So you have a couple of items. On the left-hand side or the left-hand rectangle, we have components, connectivity, and settings. So GIS. A lot of these models, if you go back to the first slide, you see the Synergy Electric overview. That sort of circuit visual, that's what I would refer to as the GIS. So that's fed into a distribution model. In addition, you have power flow measurements. Now, a couple of things here are mentioned, SCADA and AMI. There's many types of power flow measurements, but those are two common ones that are typically fed into a distribution model. And from an environmental data perspective, you have temperature and irradiance. Those are fed into a distribution model. Those, just for some context, likely associated with PV performance, where that intensity of the sun is very important, or for electric components, right? The temperature, the ambient temperature is important. You want to see what heat does to your equipment, and we'll talk about that in a little bit as well. Next slide, please. Okay, now so thinking about GIS, so whenever there's an import of GIS into a planning tool, what carries over with that is usually component information. So what you see here on the slide is a screenshot of a Synergy Electric sample model where we're looking at the subtran or at the source. So think of it as the could be the distribution subtran or perhaps could be the subtransmission subtran. That being said, normally there's a couple of components or devices included here. So you have sources, lines, devices, um, all that good stuff. And as I mentioned, when the GIS information carries over, a lot of useful information is provided. So you have component type, the type of connectivity, and in some cases, the location data. And so when these modeling softwares are taking in the GIS information, they typically use an equipment database for the component nameplate information. So you'll have transformer banks, you'll have cables, you'll have conductors. In some instances, you could have maybe inverter models. So all of that information, along with the ratings, the impedances, the kVA, the kilowatt, whatever electrical characteristic is required, these modeling softwares house that in a database. And the last point here, when it comes to the transmission source, so the engineer may need to model a transmission source and a substation to represent the overall source. So a lot of time, if let's say a utility doesn't utilities may not do the step down transformer modeling, and that will be something where an engineer would be responsible for doing that. And essentially, through that, they would determine Thevenin impedances or voltages on a lower voltage level. So just a couple of this is one sample screenshot, but there's many screenshots that show this information and how it's carried over from GIS. Next slide, please. Okay, so now let's talk about load data sources. So there's a couple of, we've been kind of mentioning them as the presentation has progressed, but there's a couple of load data sources that can be used in the modeling. So one of the options is SCADA. So as we refer to as supervisory control and data acquisition. Now that can provide load and voltage values, and normally that's measured at either the substation transformer or even at maybe the circuit breaker or the very beginning of the line. I mean, this is where we typically see the SCADA information captured. AMI is different than SCADA. This is more specific. So as the name, Advanced Metering Infrastructure, it provides you information from a customer meter demand data. So we're no longer looking at the feeder head. So if you look at the right-hand diagram, historically, load has been captured just at the black box at the very top. And the visibility downstream used to be a little limited. But now with AMI, where the triangles are and where the labels are for customers, you now have that information. So those are two known factors. Other elements here, forecasted load growth, that's normally developed and maintained separately because we don't want to bake in a load growth value with SCADA or with AMI. We want to make sure that we can basically separate what's known versus what we don't know or what we're anticipating to know. Some other things that are also shared with the load data sources. So GIS can provide customer connectivity. So the GIS can give you the configuration of the transformers. What's the high side? What's the low side? What's in terms of voltage or even configuration. It provides information like what can be the secondary cable. So it just really depends how a utility would set it up. But I would say most of the time the GIS can share that customer connectivity, at least the transformer information, fairly accurately. Now, the last point here on this slide is accurately modeling large customers. Now, with high demand, that is important because if you consider large load customers with respect to maybe neighboring customers, the large customer is going to have a much more significant impact on the power flow. So, in the power flow in the localized area. So, because of that, it is important to get actual or to, as accurately as possible, model that large customer so that you can be confident with whatever simulation results are being generated as a result of that customer. Next slide, please. Okay, now modeling DER. So there's a couple ways this could be done. So when it comes to modeling DERs, DERs are generally modeled as standalone components in distribution models. Sometimes you get a little more detail with the DER modeling Sometimes there's a step-down transformer, sometimes there's secondary cable, but for the most part, it's a primary interconnection of the DER to the system model. Now, some of the things here when it comes to modeling DERs, it can be complex because they are variable in nature, especially depending from different generating types. So for solar generation, that's only available when sunlight is available. So if you have, say, a PV system and it's tracking the sun, those hours typically are 8 a.m. to 6 p.m., depending on where you reside, if you're in the United States. For energy storage system, it could be a little difficult to predict because there's many use cases. Sometimes these PV systems can charge the BESS systems, and that's one function. Another function could be that the BESS system is going to charge from the utility grid. So it's really important to understand what sort of energy system is being installed and what is the function of the energy system. And last thing I do want to touch on here for this slide, or I guess second to last thing, would be that the DERs also do have an element of fault current and protection that do need to be considered. So during a subtransient or a fault condition, these DERs will inject fault current into the system and will have an effect on upstream protection devices and overall system the system characteristic as it relates to fault current. So that's something that we can't necessarily ignore. We have to think about the power flow impact, but we also have to think about the fault current impact as well. And one of the things here, so the last point I'll mention, when it comes to generation, it's going to be important not to double count. And we'll talk about this later, but where this becomes a problem is where you have queued generators that aren't yet connected to the system. It's known that they've applied. Maybe they have a study, maybe they've received result, but because it's not actually constructed, it's not included in the model. And so you have this phase where you have projects that haven't applied, projects that have applied, and projects that are connecting. So as an engineer, it's important to just be mindful of the interconnection queue, because if you miss a generator or perhaps you count a generator, you risk an inaccurate power flow model as well. All right, next slide, please. Okay, so this one here for middle source interoperability. So middleware is referred to as software that essentially feeds data and information from relevant sources into the model. So each of these software vendors normally provides tools or scripts to pull from multiple sources and therefore to import it into their model. So one of the examples here is SIME Gateway, which is one of the methods by which the actual SIME model is populated with those electrical characteristics that we had mentioned earlier. Now, this can be a complex process because of the amount of data that has to be transferred from the different sources. So you're looking at many elements, GIS, SCADA, AMI, and DER applications as well. So just something to note. Next slide. Okay, tools and methods. Next slide, please. Okay, so for the model setup, here we have load allocation. So essentially 3 methodologies are highlighted here. So load allocation is what we refer to as the process of distributing the measured loads at the feeder heads or even at the meters, and essentially allocating it within the model. So the 3 that are mentioned here are connected capacity, build kilowatt hour, and actual demand in AMI. And so on the graphic on the right-hand side, you kind of have a mix of things. At the substation, you have that aggregated load. You have a couple meters there with large loads or primary meters, a couple of line devices, a couple of DERs. So kind of a mix of elements here in terms of inputs. Now, the load allocation is important because you have to consider all of these inputs or all of these devices and how they would affect the connected capacity or the actual demand and how it could affect the actual power flow result as well. Next slide. So here we just have a couple of visuals. So this one is connected capacity, and all of these, most of them actually have sort of like a prorate or a ratio percentage. So in this instance, you have so for the feeder, a connected capacity value of 2000 kVA, And we know that the aggregated demand as measured is 1,000, so that allocation factor is 50%. So for each spot load, it's rated for 200. If it's rated for 200, it'll be allocated half of that. And you see that across the various transformers here on the graphic. Next slide, please. For billed kilowatt hours, so this is used in an instance where maybe utility doesn't have the best visibility, or maybe they just have better visibility on energy consumed. This is also a prorated value where if you know what the measured demand is, and you know what the total the overall feeder kilowatt hour is, you can do a ratio. So customer number one, the ratio of its kilowatt hour compared to the feeder kilowatt hour ends up resulting in a 6 kilowatt allocation. So that's a little bit about build kilowatt. Next slide, please. And for actual demand, so this one here is one of the most accurate, in the sense that what's actually measured at the meter is what is allocated to. And this is more referred to, I would almost think of this more as a bottom-up approach, where you add up the customers on the feeder, and at the head of the circuit, that is what the aggregate measured demand is. So in this instance, the addition of 5 customers ends up aggregating to a total of 102 kilowatts. Next slide, please. Okay, now for here, so just an overview of the allocation method. So they each have their pros and they each have their cons. So for the connected capacity method, kind of as I've been mentioning, the demand is normally measured at the head of the circuit, and it's distributed proportionally across the circuit using service transformer ratings. Now, the limitation here is that you may have the potential for allocation to not be accurate because the load is not always proportional to the transformer rating. You could have a lightly loaded transformer or a heavily loaded transformer. For the build kilowatt hour method, for this, the demand here is measured at the head of the circuit, but it's from the perspective of kilowatt hours consumed. And so this is often used when you have that monthly customer billing data, and it's pretty good for if you were thinking about this from the historical perspective. But where you run into limitations here is if you needed to do more advanced analyses like time series analysis, or if you have other elements like DERs, it's a little bit hard to remove the DER contribution into the kilowatt hour value. And the last square here, the actual load method. So this one here is allocated proportionally to the meter demand, but for this, it requires a pretty good interval and even pretty good accuracy of AMI data. And for this one here, it might be actually too specific, or the term here is overfit. So it's difficult in the sense that, yes, maybe it gives you great information for today, but for the future, it might not be reflective of future conditions. Next slide, please. Okay. Now for power flow analysis, so in this instance here, so power flow analysis is used to determine the voltages and currents during steady state operation. And we also have protection analysis. And as I mentioned earlier, protection studies are based on the response to short circuit conditions or even fault current. And one of the key distinctions when it comes to power flow, you get into the nuance of balanced versus unbalanced power flow. And what the graphic is showing on the right is for the top, when you have a circuit with balanced load, you have 100 kilowatts evenly distributed across the 3 phases. But on the bottom, you have it's not, the values aren't specified, but imagine that maybe one phase is loaded higher than the other. Now, while the total is still going to be 300 kilowatts, you have a little bit of an issue because there's potential when a system is unbalanced, that means that the performance is going to be different across the 3 phases. And running an unbalanced load flow could be a little difficult because it could be hard to validate the actual loading per phase, especially if maybe GIS or phase mapping isn't reliable. And the other thing that should be mentioned is while it is more accurate, it's more difficult versus if you maybe did a balanced load flow, you can essentially avoid the validation of the GIS connectivity. The one issue I'll note though is it doesn't present an actual representation on a per phase basis, so it's a little uncertain when it comes to running the balance load. Next slide, please. Okay. And for the time series load flow, so what this is, so it's essentially a power flow being ran over multiple hourly iterations. It is more complex in the sense that you need to have a large amount of data, and furthermore, you need to have very accurate data. Two common time series analyses that are done is 576, which consists of two 24-hour days per month for a year, and it normally identifies a monthly peak and minimum, versus the 8760. That one is basically 1 hour over the entire course of a year. And typically, where you see these analysis or what these power flows inform is, you can see on the right-hand side here an example of a 576 analysis, basically showing curtailment requirements of a DER. So that's where you would have time series power flow being a useful tool, or even a useful analysis to consider. Next slide, please. Okay. Now, when it comes to the training resources, so a couple are listed here. At the very top, we have the MillSoft distribution modeling training for windmill. Some other things here. So you can use utility engineering manuals and distribution planning standards. And there is also the option of software vendor trainings, but that's normally only available if you purchase software. So just something to keep in mind if maybe you're looking for a vendor-specific training.
Enrique, thank you so much for going through all of that. That was a really rich presentation for what is, of course, never enough time. And yet, even with that, we are running behind on time. So I'm going to open the floor up for some clarifying questions if folks have urgent questions that they want to verbalize. And otherwise, ask that people probably put their questions in the chat, because maybe Ben can help jump in on some answers in writing. And then we can do a little bit longer Q&A after the second half of the presentation. So from our members, anybody have an urgent question for Enrique, given his
Understanding and modeling? Enrique, take it away.
Alrighty, let's go ahead and go to the next slide, please. We'll talk about the overview. All right, so for this here, distribution planning and modeling do rely on and incorporate assumptions and results from other processes. So some of these are truly out of the control of an engineer. So you can be provided equipment ratings, solar PV performance and capacity impact, and in some instances, distribution load / DER forecasting allocation. We'll talk about these as we go through the presentation. Next slide. All right, so distribution equipment ratings. Next slide. Okay, so the key question here is, what is distribution capacity? So very simply stated, distribution capacity is the amount of load that can be supported before the equipment exceeds its rated value. Now, in the example here, we're looking at a substation transformer. So maybe let's deep dive it a little bit. So in the table, you have essentially a couple of assets here: transformers, feeder breakers, and the feeder exit cable. Each of them have their respective ratings. So the transformer is 14 MVA, the feeder is 13, and the feeder exit cable is 8 MVA, and you have the respective load values. So only for the first row, the transformer, do you have an overload. So essentially, the load exceeds the rating of the asset. And so that's what we would consider to be a overload of the equipment. Next slide, please. Okay. Now, there's a couple of things that go into the rating of the equipment. One of the most significant factor is that energy produces heat. And so because of the heat, which builds up over time, that raises the equipment temperature. So a lot of it is really based on the heat or the energy that is going through the equipment. So normally, equipment ratings are based on an allowable maximum operating temperature. And it's essentially a relationship of degradation of performance or risk of equipment failure. So some of the examples provided here, we have 65 degrees Celsius for a rating on a transformer installation, or we do have an ANSI C57.91 standard for oil immersed transformer and regulator rating calculations. So a couple of things to note there. Now, the equipment ratings, usually in units of MVA or amps, are calculated based on factors that influence temperature rise and temperature withstand capability. So a couple of things. So we have ambient temperature assumptions, equipment heat dissipation dynamics. So this is where you can get a little more rating out of the equipment through the use of fans, wind, oil circulation, multiple cables. So there are strategies to get more out of these equipment. And the other element to consider here would be conductor sag limitation as it relates specifically to overhead wires. Now, the rating calculations vary for each equipment and are usually stated by the they are stated by the manufacturer, but in utility practice, the utility may deploy fans or something of the sort to get additional capacity beyond what the manufacturer specifies out of the shop. Next slide, please. Okay, so when it comes to the types of equipment ratings, so there's a couple of different ratings, even for the same piece of equipment. And really what it comes down to is the conditions in which the equipment is going to be run. So you can see here, we have two ratings, the normal rating and the emergency rating. So the normal rating is essentially what is the rating of the equipment under everyday loading levels that can be sustained indefinitely without equipment damage or without accepting a degree of risk for the degradation of the device. The emergency rating is a loading level that can be sustained temporarily, but it's very specific. And it's normally done for instances where maybe there's an outage restoration or maybe there's some circuit contingencies or circuit abnormalities going on. And typically, manufacturers or utilities will provide a emergency rating. So here you have a couple of hour intervals, 2, 4, 8, 12, 24, 48. The one I'm most familiar with is an 8-hour rating, but again, it just depends utility to utility. And that's kind of what the next point alludes to, right? Is that utilities are willing to accept a level of risk based on their analyses, and again, it just really varies on whatever degradation and risk that they're willing to accept. The other element I'll mention when it comes to equipment ratings is when you have maybe a utility that is subjected to extremes in both the summer and the winter. So you have a summer rating for the equipment and you have a winter rating for the equipment. And so the last point here, some utilities, if they're exclusively summer peaking, there's no reason for them to use the winter ratings due to a lack of historic need. You are seeing in some areas there is change in the climate. So now there is a little bit of a pivot away or a pivot for some utilities. Now they might have to introduce the concept of a summer rating, but just something to keep in mind there. Next slide, please. Okay. So impact of increasing peak temperatures on equipment rating. So as I mentioned, extreme heat events are increasingly severe with peak temperatures expected to continue increasing. So the graphic here, we're basically seeing the increase in heat in this particular region. Looks like the Pacific Northwest and parts of Canada here. And when that happens, the ambient temperature assumptions during summer peak may need to be adjusted, which will reduce rated capacity. So as the temperatures increase, and if you consider this area, maybe the capacity values that have been specified no longer apply, and there needs to be a revisit. So just something to keep in mind as the climate changes that could have a effect on the capacity values that have been specified historically by these utilities. Next slide, please. Okay, so now we're going to pivot into a discussion of solar PV performance and distribution capacity impact. Next slide. Okay, so a couple of terminologies here, so that should be considered. Net load, so it's the amount of load measured at any given point in the feeder breaker. You also have the concept of hidden load or masked load. So that concept is essentially the amount of load that DERs are offsetting, but it's not quite apparent or it's not quite as obvious. There does need to be some reverse engineering to unmask the masked load as a result of the DER. And there's also the concept of the gross load or the native load. And that kind of touches on the point that I had mentioned, where it's the total amount of load operating with the estimated hidden or mass load added back. So there's a simple formula there where you have the gross load is equal to the net load profile plus the DER profile. So that's more or less mimicking if all DERs went away simultaneously, what is the system actually carrying? And that could be useful worst case planning when it comes to having the utility perspective on load. Next slide, please. Okay. Now there's normally a few practices done by the utility. So one of the typical practices, number one, is to plan to the gross load. So for this sort of planning, you assume that there's no DER, that there's no DER production at peak, and that there's no DER capacity contribution. So that's pretty much a worst case scenario for that one. Some of the other practices, the number two, would be to plan to the net load. So for this, you are assuming that there is DER productions in your load values, and that does embed DER capacity contribution if you plan to the net load. Now, because practice one and practice two seem to be opposite approaches to each other, one of the emerging practices that is coming is the practice of implementing what's called PV dependability. So this is now doing an estimation of reliable PV production. So this is taking into account some profiles to actually to establish basically a baseline contribution of DER performance into a system. So this is putting some shapes behind DERs. What you see here on the right-hand side, these are essentially profile shapes from some of the regions, some utility regions. So for this one here, they call it desert region. That would be essentially the shape of the DERs. On the bottom would be the Metro West region. So that's sort of a practice that aims to have a middle ground between the gross and the net load planning methodologies. Next slide, please. Okay. Now, when it comes to the solar performance and distribution section here, so some of the input data sources are SCADA data or measured SCADA data or actual historical data when it's available. But in the instance that you don't have SCADA data for these DERs, there are tools out there such as NREL's PV Watts, which use a typical meteorological year. The issue with that, though, is that it's not synchronized to it's not location specific, but at the same time, it's better than nothing. So it's a very useful tool, and I shouldn't even say that it's better than nothing. It's a pretty nice tool in the event that you maybe don't have any visibility on your DERs. If you want to gain some of that back, NREL's PV Watts could help you do that. Last thing here, so when it comes to having visibility, so the granular estimates of the PV performance from historical weather can be challenging, especially given volume or even just given locational specificity for the PV systems. Next slide, please. Okay, now let's highlight here the SCE PV dependability methodology. So this methodology was developed by using actual behind-the-meter PV data. And at the SCE utility, there are different profiles depending on the geographic region. The profiles are also broken down by the seasons, summer, winter, spring, and fall. And the risk or the accepted statistical percentile here is going to be a 10th percentile. So not crazy, not something higher than that, but 10%. Now, as I mentioned in the previous slide, you do here have the shapes. So if you desert region here, you can see that the percent profile of the DR contribution is much higher. It looks like in the summer it peaks at above 40%, versus if you considered Metro West, which is maybe I believe this is closer to the coast of California, you have a lot lower, 25%. So just to really showcase the point there that the PV dependability is different from region to region. Next slide. Okay, now when it comes to the dependable PV profile development for percentiles, so here we take the aggregate hourly PV profiles for the season by hour. And then based on that, the percentiles of performance per unit of each hour are calculated for various degrees of dependability. So that concept of dependability is just, again, how 10 percentile. So this value is greater than 10% of the lowest values. That is the risk that the SC utility has decided to take for this one. That percentile could be changed, but again, that's more risk being accepted. But that again, that's the SC methodology, and this is so the last point here. Used by scaling per unit performance for individual feeders of substations based on the total nameplate PV. So in this instance, if you have, say, a lot of DERs on your feeders, you can incorporate the PV profile to get a more per unit performance of each DER, and it's a way just to get more accurate, more specific, instead of assuming just maybe a 100% contribution at all hours of the year. Next slide. Okay, so now let's go ahead and talk about distribution load and DER forecasting allocation. Next slide. Okay, so there's two forecast methodologies that are typically present here. So for the transmission, it typically uses a top-down system peak load allocated to transmission loads. So thank you. Okay, so transmission again allocates using a top-down methodology. So the risk here with this top-down methodology is it may or may not incorporate DERs from the distribution perspective. In addition, it's a coincident forecast with various assumptions. So it considers weather, EV, etc. Versus distribution, it's typically localized. So at the distribution level, you have the bottom-up approach. And so if we think back to earlier in the presentation, if you have, say, maybe the meter information or even the recloser information or just sort of more circuit-specific information, you can develop a load forecast using those elements and basically build your way back up. So the graphic here on the right-hand side, I would say is pretty useful in visualizing that. So if you're at the bottom-up approach, you can see there we have load, DERs, builds up to distribution circuits, builds up to distribution substations, builds up to transmission nodes, and from the top-down approach, you have a system forecast, and you basically have transmission nodes. So transmission and distribution will meet at the transmission load section, and the hope there would be that there's somewhat of a match between the two forecast approaches. Next slide, please. Okay, now in terms of DER disaggregation techniques, so there's a couple that I should mention. So there's the proportional allocation method, which is basically it allocates system level DERs, DER forecasts to individual circuits using specific local distribution data. And so this one here, so the other point I'll mention is another approach is to use adoption patterns of one technology to drive adoption for the other. So that's proportional allocation. You also have the propensity models. So for these, the propensity models use the customer characteristics to compute a propensity score. And based on that score, fraction is computed as the ratio of the score. And I guess the example here, so you can, if you're using propensity model, that can be estimated using zip code data where the models relate historical adoption to customer characteristics in each zip code. So it's a very statistical based approach where you use a couple of machine learning or I guess statistical methods like linear regression or even other more advanced machine learning models. And the last one here would be the adoption model, which uses the bottom-up adoption approach based on the adoption patterns and estimated adoption model parameters. And this sort of model is S-curve based, where it forecasts technology adoption based on characteristics of early adopters, market factors, adoption rates, and it's applied to the remaining potential. So that's, again, sort of an overview here of the DER disaggregation techniques. Next slide, which I believe takes us to the Q&A section.
Great. Thank you so much, Enrique. That was